Here's a screencast on nanotechnology. At the end of the screencast, the minimum, you should be able to define the term nanotechnology, distinguish between both physical and chemical techniques in manipulating atoms to form different molecules, describe the structure and properties of carbon nanotubes, and discuss some of the implications for society of nanotechnology. So the first thing we should probably talk about is what does it mean for that nano kind of prefix. And if you remember, which we don't do a whole lot of, but nano is a prefix in the metric system, meaning 10 to the negative ninth. So nanotechnology is really the research and development of technology in the 1 to 100 nanometer range. Very, very small. How small is it, might you ask? Well, 1 meter is 1 times 10 to the negative, or I'm sorry, 1 times 10 to the ninth nanometers. A micro, this should say micrometer. It's this one. Oh, no, I'm full of crap. 1 millimeter is 1 times 10 to the negative sixth nanometer. So in 1 millimeter, smallest division on a metric ruler is 1 times 10 to the sixth, or a million nanometers. 1 micrometer is 1,000 nanometers. 1 angstrom, 10 angstroms, is 1 nanometer. So hopefully that gives you an idea of how small a nanometer is. We can relate nanometers really to atomic and ionic radii of elements. Looking at hydrogen has a radius of 154 picometers. Okay, pico is 10 to the negative 12th. Okay, so 154 times 10 to the negative 12th meters. Okay, and you can go up to larger ones, 222 picometers for things like arsenic, 245 for antimony. So you get the idea that, and I'm talking about ions here, the atoms are up here. Very, very small scale, things that we're not going to do with the human eye. Right? Continuing, football, because it's European, 22 centimeters down to a buckyball, which is 0.8 nanometers. Okay, buckyball is a sphere of carbon atoms that are in a hexagonal and a pentagonal arrangement. And I think we talked about buckyballs way back when we were doing bonding and structures. So, why even bother doing nanotechnology? Well, because we can introduce unique properties at this scale. And as technology has progressed over time, we've been able to work with things that are smaller and smaller. At the advent of computers and advanced instrumentation, we can actually work at that atomic or molecular level. Okay? And unique physical properties, electrical properties, and interaction with light are all unique properties that can be manipulated at that scale. How to make nanomaterials? Well, there's kind of two strategies. Top down, okay, breaking larger particles into smaller ones, or you can build them bottom up from individual atoms. And this is the approach most often taken with nanomaterials, because building from the bottom up, you can manipulate atoms in the structure physically, meaning manipulate them with instruments to place atoms where you want them. And we can also use chemical reactions to position atoms. And we've seen reactions of that type when we were discussing polymers. All right. So physically, with instrumentation, placing atoms where you'd like them, and through chemical reactions like the reactions we saw in polymers to position atoms along a molecule. In 1986, Gerd Binnig and Heinrich Rohr developed the scanning tunneling microscopy. And this images the surface of materials by scanning them with a very fine stylus, okay, tunneling electrons. Okay, so they were actually able to generate pictures, if you will, or representations of atomic arrangements of atoms. And you can see the different atoms as being little spheres in this 13 nanometer by 13 nanometer square of material. And this is the actual buckyball class of carbon structures. Fullerenes is the overall term for these structures, and those were first discovered in 1985. And this kind of led to the advent of nanotechnology. Nanotechnology, a lot of times they're just doing these nanotubes of carbon. The walls of the tube, the main section, consist of hexagons of carbon atoms, covalently bonded along the tube length. The tube ending, the cap, is a pentagon. Okay, so they have to kind of close that down using or close the tube using a smaller structure of that carbon ring. The great strength of your nanotube lies in this section. Okay, and this is, greatest strength is right here. Greatest strength. Okay, and this is primarily due to the carbon-carbon covalent bond. And giving rise to this very regular crystalline structure. And that's pretty much where the strength of that carbon nanotube comes in. Okay, so it is important to realize that the carbon tube length is hexagonals, or hexagons, closing the cap with a more with pentagons in that carbon structure. The interesting thing is you can also make like a test tube. Okay, by only closing one end. And when you do this, they tend to say that it's closed with a Fullerene cap. Okay, and that really, you have one end open and you can kind of use it like a molecular scale test tube. That's pretty cool. The other thing that's kind of cool is that you can introduce silver chloride into the tube and then decompose the silver chloride, and you basically line the tube with silver. Hopefully, you thought, oh, hey, lining it with the metal. That would make that very electrically conductive. And keep in mind, you're doing all these things with something that is on the scale of 1 to 100 nanometers. Physical properties of these nanotubes. High tensile strength. The nanotubes are said to be 50 to 100 times stronger than iron. And that's, again, due to those covalent bonds in that tube, that hexagon structure. They have low density, high melting points, high thermal conductivity, and they are electrical conductors or semiconductors, and those properties tend to depend on the length of the tube. Nanotubes are also used as catalysts. Why would they be useful? They have a very high surface area. Keep in mind, if you have a quantity of nanotubes that you can actually see on a macroscopic scale, it's made up of tubes that are on the order of 1 to 100 nanometers. So there's little tubes. It's a ton of surface area. And if you're asked a question about catalysts and nanotubes, make sure that you use the words high surface area. Okay? And the size of the opening in those nanotubes make them very selective for certain molecules. Okay, so you can manipulate these tubes, because remember, we're manipulating them on that atomic molecular scale, so we can make them to be very selective for certain molecules. Other uses for nanomaterials: for agriculture, non-porous zeolites for slow release of water and fertilizers. For healthcare, you can use nanosensors as diagnostic tools. For energy, those catalyst enhancing fuels for better efficiency. Electronics, that's why everything's so small these days, because you can make electronic components out of nanotubes. Okay, ICT, flat panel flexible displays, faster processing computers. Water treatment, we can have nanomembranes for water treatment to filter impurities out of water. So we've got to tie the nanotubes into both positive effects, and then we'll be looking at some possible negatives. Positive effects are those growths in new industries. Okay, it's a whole new sector. Who knows what the growth will be. An improved quantity of life due to developments in technology. This really translates to faster computers and electronics. Nanotechnology. There are health concerns because it is like unknown. It's an unknown, unproven, not developed on any large scale. Toxicity is part of this health concern. The effects of nanomaterials have not been tested. Current regulations are not applicable to these materials, because typically this toxicity is based on a concentration of materials, and it's materials of size that we know of. So the nano, it doesn't relate to nanomaterials with those concentrations, okay, because it's based on concentrations of current materials and sizes of those materials. Safety of nanotechnology is also a concern, because these fine particulates are usually more likely to cause explosions. Explosions. Okay, so this is more in the manufacturing and the storing and transferring of materials. Employment implications. There's going to be a shift from current industry to new industry. So workers may have to be trained differently for this new technology and manufacturing processes. So you may leave people without jobs if we continue to cross over into nanotechnology. It's also likely to increase the divide between wealthy and developing nations. The wealthy nations are going to have the capital to invest in the research and development, with the developing nations lagging behind. And then there's also sometimes a lack of public involvement in policy discussions. leaving it up to scientists. And sometimes people are driven by greed and don't take into account public health and safety. Right? So that's the end of the screencast on nanotechnology.